Our presentation now is about circular functions. In this case, we are trying to get functions which will deal with or describe functions or phenomena which occur in a circular way. But I think everybody will remember this from school. What is that? A protractor, isn't it? Yeah, that is a protractor. And when you talk of circular, you are talking about something which moves like this. As you can see there, every point is moving except one. Which one is not moving? The center, isn't it? So we say something is rotating. Then once we talk about that now, then we start talking about new things like angles. My teacher, I don't know what your teacher told you when you went to school, or maybe you can try to tell me what your teacher told you before I tell you what my teacher told me. What is an angle? Or what does an angle tell you? Angle tells you exactly what I've just stated. This is what I was told by my teacher. My teacher said an angle is amount of turning. It's an amount of turning. So one way we measure that amount of turning is choose what I've just written there, what we call decrease. 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 All together. But today, I'm going to put in some kind of conflict with decrease. I'm going to show you somehow that decrease do not always work. Maybe I might have a funny comment from some people about this one. For me, it seems to me, according to how I read history and how I see things, decrease actually came about because of certain beliefs which certain people had. Things like believing that the sun moves around, I don't know whether the earth moves around the sun in 360 days, like the earth, during that days and night rotating, it has got a route which it follows around the sun in 365 and a quarter days. These days, that's what we believe. But before, it looks like people believe that it takes 360 days. So since that kind of motion is circular, to get a measure for the turning, they decide to divide the circle into 360 parts. And then they called each one of those parts decrease. But decrease in practical, in some very, very serious calculations, and even simple ones which you do in school, decrease don't always work. Do you want to see that? That they don't always work? Are you serious? You want to see it? I will show you that decrease don't always work. Okay, so what will work is what we're going to talk about in a few minutes' time. All together. What will always work is what we're going to talk about. Now, what I'm trying to say to you, get prepared now. Today, you are going to learn a new way of measuring angles instead of decrease. All together. I'm not saying we're going to throw decrease right through the window. Where they work, we're going to use them. Where they don't work, we must resort to something else. All together. Okay. So let's see. Here is the situation. Let's say that is a circle. With a radius, in this case, I will choose a special radius and say it's 1. Maybe let's say 1 centimeter. If I take an arm like that, like this radius, and turn it to 0 here, and turn it to there, and turn it to there, I think you can see up to there, I've moved what we've always called right angles, and that is a quarter of the turning, isn't it? Okay. Now, if I call this length here arc S, let's say the length of that arc is S. I think it's clear also that that S is also a quarter of the whole circumference. Altogether, it's clear to go. Okay. So I can claim this thing. I think it's true. I can say this. I can say the circle is a fraction of the circumference. Is it true? The arc is a fraction of the circumference, isn't it? So I can take the arc, the length of the arc, over the length of the circumference. That fraction, that is a fraction. I'm saying the arc is part of the circumference. That's true. That's how we deal with rational numbers. So now, but I can say this fraction this angle, let's say this angle, in this particular case is 90 degrees, but I don't want to talk about 90 degrees per se. I just want to talk about any angle theta. If I open this much, the fraction of which the length arc is of the circle, there is also a fraction that to the whole revolution. In other words, the revolution, I'm meaning what? The turning right round, is it? Now these two fractions, how do you want to compare them? Are they equal? Are they equivalent? What do you think? If I move half of the circumference, I get half of the revolution. If I move quarter of the circumference, I get the angle quarter of the revolution. So how do these things compare? They should be equal, isn't it? They should be equal. So let's say these two things here are equal. Let's leave them there. Let's leave them there. But I think what you can see here, if I knew the circumference, if I knew this, if I knew that, I can say here the formula for this the arc of a circle is equals to the angle as a fraction of the whole revolution. Let me write the revolution here instead of saying r. Maybe people can confuse that with the radius. Revolution multiplied by the circumference. Let's leave that there as a formula which we've just agreed on, that it must be valid on the basis of that these two fractions are equal. All together? Okay. Now, I said degrees don't always work. What will always work, we must first know it. How does it look like, that thing which will always work? Let's see, there is the situation. Draw a circle again there. You can choose your radius 1 or any other radius, it's not a problem. Then what do I do here? I put this line which I put here. Let's suppose it's a fish line. I hope so everybody knows what is a fish line. Do you know what is a fish line? Builders use it, not fishing, they use it for building. And the fishers, they use it fishing. Altogether. So it's a line which has got more purposes. So I can use it in this situation also. It's a fish line. What do? I put this fish line in such a way that it's tangent to the circle there. When it's tangent, it touches only one point. Altogether. We must not see it with our naked eyes, but we must imagine it. Altogether. We must imagine seeing that line touching the circumference only at one point. Which is difficult but possible. Imagination is the most powerful things you can ever have. My friend, listen, all what you see around here, even writing on the screen like this, it started as an imagination of human beings. So if you want to praise God for something wonderful which ever gave to people, is the power of imagination. Planes are flying, they shoot them down, unfortunate, but planes are flying. Is because of the power of imagination. All together. So please, cultivate your imagination. It will take you to heights. All together. Yes. Good. So now, let's do this now. What we're going to do now, to make sense of what is going to happen now. This fish line is flexible. It's normal to expect it to me to hold it here and then turn it like this around the circle. It's normal. Everybody expects that. It's obvious that if I got a fish line like that around the circle, that circle could be the surface of a cross section of a drum. If I take the fish line, I can wrap it around the drum. Isn't it? Okay. So now let's take us to this situation. I've pulled that thing this way, and then the fish line now is lying that way. Just see that now as the way it was, and then see here as where it is now. All together. Now I pull this thing around the circle in such a way that the arc which is here from there to there is actually equal to the radius. Am I making myself clear? I've taken this, remember this line here, this straight fish line. I can measure the radius from there and say the radius here, I transport it and measure it up to there, isn't it? Then when I pull it, that point which was marking the length of radius falls on the circumference there. Is that true, isn't it? Yeah. Then now what we have here, we've got the radius here, the radius here, the radius there. It's like we've got an equilateral triangle which has got a bent side, but it's not a triangle, isn't it? But I'm just trying to track some similarity there. This thing has got three sides and they're of equal length, but it's not really a triangle because the other side is arc, is circular. So this angle which is here, theta, this angle, under the situation that theta there, that theta is what we're going to call 1 radian. Half of it is going to be half radian. If I take half of this length, it's going to be half radian. 1/10 of that length will be somewhere here. If I take 0 of that length, it will be there. So there, we've got 0.0 radians and or 0 degrees. So an angle which was 0 degrees will still be 0 radians, isn't it? Okay. Now, and then I continue pulling that. If I come there, I really don't know what it is. If I come right round until the fish line is looking like this, when now it's tangent there and there's tangent there, I've actually covered half of the circumference. But I think everybody knows that the circumference is 2 what? Pi what? 2 pi r or pi diameter. Are we together? Okay. So in other words, what are we saying here? When we've covered all this length up to there, we've covered half of the circumference, isn't it? Okay. So now that angle now is going to be, let's say this r is 1. Because remember, this angle is not going to change because of the radius of the circumference. Are we together? If I draw another circumference there, it is another circle which is bigger than this, but center the same center. That arc there will be reflected somewhere there, and so it will be the same. Now, if we set our radius equals to 1, radius equals to 1. Why? Because it's comfortable to write to use what? To take 1, is it? So what are we going to do now? In that formula which we had before, the circumference of this thing now is going to be what? 2 pi. The formula which we had before, it said this arc is to the length of the circumference, which is 2 pi equals to, now what is this? Is the angle which is what? That angle is what? You can just put it as theta, isn't it? You don't have to put it in particular, but it's theta, isn't it? If it's this angle now, it's going to be called theta. If it was here, it's going to be theta. It was here, it's still going to be theta. But that will be to the whole revolution. But check. This is half the revolution, isn't it? And the whole revolution, we know it's going to be 2 pi, isn't it? Okay. Then that is going to be, no. I think I've made a mistake here. Sorry. Let's leave this r here. Let's leave that r there. Sorry. Yeah, let's leave that r there. That will be the whole revolution, and the whole revolution is what? Is 2 pi, isn't it? Okay. So now, then we say here, S over the circumference, which is 2 pi r equals to theta over 2 pi, isn't it? Now if we make S subject to the formula here, if we make X subject to the formula, then we can get S equals to theta r, because 2 pi and 2 pi are going to simplify to 1, isn't it? Listen to what I said. I said they're going to simplify to 1. I didn't say they're going to cancel. I said they're going to simplify to 1. So now what happens now? This becomes a formula for calculating the length of an arc. We're right at the point where to show that this degrees are not going to work here. Let's suppose we're using degrees. and this radius is 1, like we said there. Let's say that radius is 1. And we take an angle, for example, of 90 degrees. And then we want to substitute here. What are we going to have here? We're going to have S equals to 90 times 1. And 1 here could be 1 centimeter, isn't it? And any other length must come as in centimeters, isn't it? Now what are we going to get here? We're going to get 90. 90 what? Centimeters. Do you think a circle which has got radius 1 centimeter here can have something here which is 90? Which is almost a meter. If it's centimeters, this will be almost a meter. Do you see that that number is absurd? Do you see that it's absurd? Please guys, feel it. It's here. You must feel that that is absurd. Do you feel it? It's absurd. The only reason which makes this number absurd is because we're using degrees. If we say now this revolution is 2 pi, half of it is pi. How's it? Now up to there is quarter, is half a pi, isn't it? So which is 90 degrees in this case will be looked at as half pi radians. Now if we take this S now as S equals to pi over 2 times 1. Remember at school they used to say take pi to be 3,14. How together? They said take pi to be because they knew that we didn't understand what pi is by then. But yesterday, day before yesterday, we established that pi was an irrational number, which could not be represented as something, a number over another number, isn't it? So if we take to that approximation pi to be 3,14, if we divide by 2, 3,14. If you divide by 2, we're going to get 2 into 3, 1. Carry 1 into 11, 5. Carry 1 into that 7. And then you get here, you're multiplying 1.57 times 1. And the answer will be 1.57. And it makes sense. If you've got a circle which is 1 radius, obviously the circumference is going to be longer than 1. Sorry, if you've got a circle which has got a radius of 1 centimeter, the circumference is going to be longer than 1 centimeter, definitely, isn't it? Then it's expected to get a length of an arc which is 1 something when the angle is what is 1/4 with that. It's expected. But to get 90 something centimeters is absurd. So that shows that degrees fail in some formula which we need to use. All together. So what are we going to use now? We are going to use radians. What are we going to use? Now, what we've just seen here is that pi is what you used to call 180 degrees. All together. All together. Okay. So maybe let me write here conversions. Conversion. What is conversion here? Conversion from degrees to rad, and from rad to degrees. So now if we've got pi to be 180, if we want 1 radian, I think we must divide this radian by pi. So we get here pi over pi. We get 1. And then here we get what? 180 over pi. So in other words here, 1 radian is equals to 180 over pi. All together. I don't know what I'm doing correct there. Then when we want degrees, we should divide, if we want 1 degree, we should divide this by 180. Then if we divide this side by 180, we get 1 degree. And this side, we're going to have what? Pi over 180. So now this number, pi over 180, without units like that, it becomes a conversion factor from degrees to radians. Now, take 90 degrees. Want to shift that to radians. We've got to take this factor, which I call the conversion factor. Then what I'm going to do? I'm going to multiply 90 by pi over 180. I simplify that. That shows that this converts to pi over 2. All together. Now you can go and play around now. What is your 60 degrees? What is your 30 degrees? What's all right? So now angles, 90 degrees is no longer 90 degrees when you want to record it. It's pi over 2. 306 degrees is 2 pi. All together. So from today onwards now, let's note degrees and you must, the other thing, must train yourself. You must train yourself to see where degrees are not going to work and the way degrees are going to work. Because if you don't see that, then you're going to get upset calculations, upset numbers, and so forth, so forth, and so forth. Am I making myself clear? Okay, let's see those people are saying it's clear. Those who are saying it's not clear, please, I'm prepared to repeat. All together. Okay, so guys, I hope now you are convinced it's exactly how did you get to these radians. Then when you use them, then nobody must be surprised. Because normally, when you use things in the absence of knowledge, anything will be surprising. Did you hear that? If you deal with things in the absence of knowledge, anything will be surprising. Actually, in the past, in the primitive ages, people used to be even surprised by the rain and the thunder and everything. Everything was surprising because it was in the absence of knowledge. All together? Okay. So can I close this session on what? On radians. Okay. Thank you for listening.